Welcome to the online training session day 1. In this, I am going to cover theory of FEM and CAE. The reference book, the reference of this theory presentation is taken from Practical Aspects of Finite Element Simulation student guide. To download that free copy of student guide, you can visit to http://www.alteruniversity.com/student-guide-request/. So at the end of the session, I'm going to show you how to apply for the free copy of student edition this book, from where I have taken the theory. In this training series, I am going to cover, as this is the first day, I am going to cover theory of FEM. On second day, I am going to take 1D meshing. On day 3, 2D meshing, how to create 2D meshing or how to generate 2D elements on mid surface, how to edit them. Then on day 4, 3D meshing. Then on day 5, I am going to show you the different analysis and post-processing. In day 6, we are going to discuss topology optimization. Day 7, I am going to show you topography optimization. On day 8, I am going to show you size optimization. On day 9, shape optimization, and in day 10, composite optimization. So this training series covers hypermesh, complete pre-processing, radios and OptiStruct to solvers for linear, non-linear, thermal and optimization analysis, and post-processing, which includes hyperview. So the topic for the today's training session is, first we are going to discuss introduction to meshing, where the topics will be why do we carry out meshing, types of element, how to decide the element type for a particular model, can we solve the same problem using 1D, 2D and 3D elements, how to decide element length, how to start meshing, meshing in critical areas, then 1D meshing, when to use 1D elements, types of 1D element, then theory of 2D meshing. In this I am going to cover when to use 2D elements, family of 2D elements, that is the types of 2D element, how not to mesh, what are the different industry standards which you have to use while doing the meshing. So what are the different things which industry people follow while they do meshing. Then 3D meshing, when to use 3D elements, degree of freedom for solid elements, as there is a slight change in degree of freedom for solid elements. Then how not to mesh for 3D meshing. Then elements quality check, general element quality check, particularly for 2D qualities, 2D meshing or 2D elements quality check, other checks for 2D meshing, quality checks for Tetra meshing, that is 3D element, other checks for Tetra meshing, brick mesh quality checks, again this is a 3D element, other checks for brick meshing. Then lastly we are going to discuss material and property information, in which material classifications and material properties. So these are the topics which we are going to discuss. They are very important to start with any CAE software. So basically CAE software has their own engineering knowledge behind them. So to understand the basic principles of these CAE software, how they work and what is the basic engineering required to understand the behavior of any CAE software, this theory portion is very, very important. So let's start with introduction to meshing. So the first question arises, before entering to anything or before going for CAE, the first question arises is why do we carry out meshing? So the basic idea of FEA is to make calculation at only limited finite number of points and then interpolate the results for the entire domain. It may be surface or volume. Any continuous object has infinite degrees of freedom, and it's just not possible to solve the problem in this format. Finite element method reduces the degree of freedom from infinite to finite with the help of discretization or meshing, that is nodes and elements. So as in this problem, you can see this particular circle having infinite points, and if we calculate 6 degrees of freedom per point, so the total equation to be solved is infinite. That is not possible. But if we discretize this with say 8 points like this, so at each node we have 6 degrees of freedom, so the total equations become 48. That is quite possible to solve. So in this way, that is why it is required to do FEA. So to discretize the degrees of freedom from infinite to finite, it is not restricted to number of freedom 8, number of nodes to 8. It may be 10, it may be 4, but it's just an example. Then we move to the next, that is types of element. So there are different types of elements available, starting from 1D. We define 1D as one of the dimension is very large in comparison to other two. In 1D, the element shape is line. Additional data from the user required is remaining 2 dimensions, that is area of cross section. Then the element types available for 1D element is rod, bar, beam, pipe, axisymmetric shell, etc. And practical applications are long shaft, beam, pin joints, connection elements, etc. Then 2D elements. The 2D can be defined as 2 of the dimensions are very large in comparison to the third one. Element shape for 2D meshing is quad and triad. Additional data from the user which is required is remaining dimension, that is thickness. Element type: thin shell, plate, membrane, plane stress, plane strain, axisymmetric solids, etc. The practical application of 2D elements or 2D meshing is sheet metal parts, plastic components like instrument panels, etc. Then 3D elements. For a 3D elements, all the dimensions are comparable. The element shape is tetra, penta, hexa elements or pyramids. Additional data from the user, there is no additional data required from the user. Then element type is solid. Practical application is transmission casing, engine block, crankshaft, etc. There are some other types of elements are also available, like mass elements, which is known as point element, concentrated mass at the center of the gravity of the component. So to put a mass or to put some additional weight to your component, you can use that. Then spring elements, translational and rotational degrees of freedom, that is translational and rotational stiffness. To simulate that, we can use spring elements. Then to simulate damping coefficient, we can use damper elements. To simulate gap or gap distances and stiffness friction, we use gap elements. To transfer the forces or constraint from one bolt location to another, we use rigid elements like RVA2, RV3, and then to simulate welding, we use weld elements. So these are the different types of elements available. Then The next question arises is how to decide the element type. Say for a particular component, how we can decide what type of element should we use. So the element type selection can broadly be classified as geometry, size and shape, type of analysis, time allotted for the project. So first is geometry, size and shape. We will discuss one by one all. So for an analysis, the software needs all the 3 dimensions defined. It cannot make calculation unless the geometry is defined completely by meshing using nodes and elements. So the geometry can be categorized as 1D, 2D or 3D based on the dominant dimensions, and then the type of the element is selected accordingly. Say for example, 1D element used for geometry is having one of the dimension that is very large in comparison to other 2. If you see such type of geometry, then only you can use 1D elements. The shape of the 1D element is line. When the element is created by connecting 2 nodes, the software knows about only one out of the 3 dimensions. The remaining 2 dimensions, that is, the area of the cross section, must be defined by the user as additional input data and assigned to the respective elements. Practical example is long shaft, rod, beam, column, spot welding, bolted joints, pin joints, bearing modeling, etc. So as you can see in this model, the length is very large as compared to its cross section. That's why we can use this for 1D element. Then for 2D element used when 2 of the dimensions are very large in comparison to the third one. So in any of the geometry like sheet metal components where the thickness is very less as compared to other 2 dimensions, then we use 2D elements to simulate that kinds of problems in FEA or CAE. So 2D meshing is carried out on a mid surface of the part. 2D elements are planar, just like paper. By creating 2D elements, the software knows 2 out of the 3 required dimensions. The third dimension, that is thickness, has to be provided by the user as an additional input data. Then a question may arise, why to create 2D, why is 2D meshing carried out on a mid surface? We can use any of these surface, either the top one or the bottom one. Why we have to create a mid surface and then do the meshing at the, then do the 2D meshing on it? So mathematically, the element thickness specified by the user is assigned half on the element top and half on the element bottom side. Hence, in order to represent the geometry appropriately, it is necessary to extract the mid surface and then mesh on the mid surface. So in practical example, all sheet metal parts, plastic components like instrument panel, etc. In general, 2D meshing is used for the parts having width to the thickness ratio greater than 20. If the width to thickness ratio is greater than 20, we use 2D elements. So as you can see in this component, the 2 of the dimensions are very large as compared to the third one, that is the thickness. So we define a mid surface, and in this mid surface we are going to do the meshing so that half of the thickness will go up, half the bottom, so the plate simulation will be proper. The limitations, then we discuss about the limitations of mid surface and 2D meshing. The 2D meshing would lead to a higher approximation if used for variable part thickness. Also, surfaces are not planar and have different features on 2 sides. Like if these are at the top, if it has a different features, and at the bottom of the face, if it has a different feature, then it is also an approximation, because If we generate a mid surface, we cannot create two different features at the top and the bottom. Then we move towards the next, that is 3D element. 3D elements are used when all the three dimensions are comparable, as you can see in this. So if all the three dimensions are comparable, so there is no input or no additional data required from the user. So practical examples of are transmission casing, clutch housing, engine block, connecting rod, crankshaft, etc. As you can see, the model which is meshed using 3D elements. Then the second point is based on type of analysis. So structural and fatigue analysis, we use quad, hex elements are preferred over trias, tetras and pentas because they give the better result. Then in crash and nonlinear analysis, priority to mesh flow lines and brick elements over tetrahedron elements. So brick or quad elements are preferred over tria or tetrahedron element for crash and nonlinear analysis. For mold flow analysis, triangular elements are preferred over quadrilateral element. For dynamic analysis, when the geometry is borderline between the classification of 2D and 3D geometry, 2D shell elements are preferred over 3D. This is because shell elements being less stiffer capture the mode shape accurately and with a fewer number of nodes and elements. Then the last point to decide the type of element is time allotted for the project. When time is not constrained, the appropriate selection of element, mesh flow line and a good mesh quality is recommended. Sometimes due to very tight deadline, the analyst is forced to submit the report quickly. For such situations, automatic or batch meshing tools could be used instead of time consuming but structured and good quality providing methods. For 3D meshing, tetras are preferred over hexas because we can do meshing much faster using tetra elements. If the assembly of several components is involved, then only the critical parts are meshed appropriately. Other parts are either coarse mesh or represented approximately by 1D beam, spring, concentrated mass, etc. Then the next is, can we solve same problem using 1D, 2D and 3D elements? It is not possible to use 3D elements for long slender beams 1D geometry or sheet metal parts 2D geometry and 2D shell elements for representing big casing parts. For same geometry, the same geometry could be modeled using 1D, 2D, 3D elements. What matter is the number of elements and nodes, degree of freedom, the accuracy of results and the time consumed in the analysis. Say for example, consider a cantilever beam with dimensions 250/20 by 5 mm that is subjected to 35 Newton force. If we calculate using 1D element, the number of nodes are 2 and number of element is 1. If we use 2D shell meshing, the number of nodes is 909, number of elements are 800, so total degree of freedom is 5454. If we use 3D elements for the same problem, then total number of nodes is 17,448, number of elements goes to 9,569 and total degrees of freedom goes to 52,344. But there is no changes in the results. 1D element is giving the same result as 3D. But as the number of nodes and elements increases, the solver time also increases. So depending on the requirement of as per the geometry and as per the availability or as per the way of analysis you want to perform, decide the type of element. Then the next question arises is how to decide element length. We can do the meshing of a particular component with element size 2, 3, 4, 5, 6, 7, 4.5, whatsoever. We can pick any length. So how to decide which length is the best? So the element length is decided as based on previous experience with a similar type of problem, successfully correlation with experimental results. Then type of analysis. Linear static analysis could be easily carried out quickly with a large number of nodes and elements, but crash, nonlinear, CFD or dynamic analysis takes a lot of time. Keeping control on the number of nodes and elements is necessary. Then hardware configuration, that is very important, and graphic card capacity of the available computer. An experienced CA engineer knows the limit of nodes that can satisfactorily handle with the given hardware configuration. Suppose you are a part of newly formed CA group, no clear guidelines are available and there is no experienced person in the group. In the first run, then you can do this, like in the first run, accept the default element length, mesh it with the basic rules, then run the analysis and observe the high stress region. Remesh the localized area of the high stress with smaller element length and solve it again. Compare the difference in the original and the new results. Continue the process until the convergence is achieved, that is 5 to 10% difference in strain energy and maximum stress value between the two different element length. When this is achieved, you can pick the earlier one. So say for example, you are meshing a certain component critical zone with elements length as 8, you get a stress as 100. Then you lower down the element size to say 5 and you get a stress as 101. So there is no much difference in the two stress results. So you can pick 100 and the element size is 10 and carry out the meshing. Then the next question arises is how to start the meshing. From where exactly we should start the meshing? So to start the meshing, first point is to spend a sufficient amount of time studying the geometry. A common observation is that CA engineer starts meshing immediately without properly understanding the geometry and paying attention to all the requirements and instruction provided. Observing the geometry several times and thinking about it for all angles is strongly suggested. Mental visualization of step is the first step in the right direction of creating a good meshing. Then time estimation. Nowadays the trend is towards the client or boss specifying the estimate time for a given job to the service provider or subordinates. Sometimes it is decided based on mutual understanding. A time estimation is very relative and one can find a lot of difference in estimation by different engineers, as much as 2 to 3 times. Usually a less experienced person will estimate more time. Also, if someone is handling the job for the first time, then he or she will require more time. If similar kind of job is given to the same engineer again and again, the mesh time would reduce drastically. Geometry check. Generally, CAD data is provided in IGES format. Geometry cleanup is an integral part of meshing activity. CA engineer should at least have the basic knowledge of CAD. Before starting the job, the geometry should be carefully checked for free edges, scale lines, duplicate surfaces, small fillets, small holes, bits, intersection of parts, assembly of the component. If suppressing fillet, small holes, bit, or the generation of mid surface is required for meshing, then why isn't the CAD data provided in the way needed for CAE by the CAD engineers itself? The answer is yes. Theoretically, that would be an ideal situation. But practically, everyone works with a very tight schedule and target dates. CAD data is generated keeping in mind the final drawing to be released for manufacturing. The same CAD model is provided simultaneously to the tools, jig fixtures manufacturers, vendors, purchase engineers, and CA engineers as well. The simplification required for FEA is understood better by CA engineer than a CAD engineer. HyperWorks software provides special tools for geometry cleanup and simplifications, which are usually much faster than CAD software. Many times, for complicated geometry, surfacing operation fails in CAD software and it could be easily handled by CA engineer by avoiding the geometry and generating the mesh using manual or special meshing operations. So that's why the CAD is not designed like that. Then the fourth point is symmetric check. To start the meshing, the fourth point is symmetric check. We can check for the complete part symmetry. Meshing only a quarter of the plate and reflecting it twice is advisable. As you can see, this quarter plate, if you reflect it once, you will get a half, twice you will get a full plate. So you can also check for the symmetry. Then sub-part symmetry, repetition of features and the copy-paste command meshing. The highlighted 22.5 degree portion and then using reflection and rotation would lead to a faster mesh as well as same structure of elements and nodes around the critical area, that is holes. So we can cut a section of some angle and we can use the reflect rotate command to do the meshing, do the same meshing everywhere around the circular, as you can see in this rim for this particular rim. Then selection of type of elements. In real life, we rarely use only one type of element. It is usually a combination of different types of element, that is 1D, 2D and 3D and others. In the below figure, the handle of the bucket is modeled with 1D beam or 1D element. The bucket body uses shell 2D elements and the connection between the handle and the bucket body through RB2 rigid element. So these are the different types of elements a CA engineer uses to model a real life problem. Then type of meshing. If it's a geometry based meshing, the mesh is associated to the geometry. If the geometry is modified, the mesh will also get updated accordingly automatically. The boundary condition could be applied on the geometry like surface or edge, etc. And FE based mesh is not associative. The boundary conditions are applied on elements and nodes only. So you have to decide the type of meshing you are going to perform, geometric based or FE based. Then how to do meshing in critical areas. First of all, we will try to understand what are the critical areas. Critical areas are the location where high stress locations will occur. Dense meshing and structured mesh, no trias, no pentas is recommended in these regions. Areas away from the critical areas are called general areas. Geometry specification and coarse mesh in general areas are recommended to reduce the total DOF and solution time. Then how would I know about the critical area before carrying out an analysis? After going through a previous analysis of similar part carried out by your colleague or a senior in group, one can get a fairly good idea about the probable location of high stresses. But suppose there is no past record, and you are doing it for the first time, then run the analysis with a reasonable element length and observe the result. High stress regions are critical and could be remeshed with a smaller element length in the second run. Rules for modeling holes and fillets. So critical areas are circles, so minimum 12 elements around the hole, or general areas 4 to 6 elements will also work. For critical areas, the fillets, minimum 3 elements on the fillet. You can, for the general areas, you can suppress the small fillets, or 1 element for large fillet will work. Also, mesh transition techniques and flow lines. There is different mesh transition techniques like 1 to 3, 2 to 4, 1 to 2, or like 1 into 2 by 2. Then we will start with 1D meshing. So now the question arises, when to use 1D element. 1D elements are used when one of the dimension is very large in comparison to other two. The element shape is line. The representation of this, it looks like line. Additional data from the user required are the remaining 2 dimensions, that is the cross-sectional area. The element type is rod, bar, beam, pipes, axisymmetric shells, etc. Practical applications are long shaft beams, pin joints, connection elements, as you can see in this. Then we will see the different types of 1D element. So we'll start with rod. For rod element, it supports only tension and compression, and torque for some softwares like in HyperWorks it supports torque also. So UX or UR, U stands for translation, R stands for rotation. Translation about a particular axis, rotation about that particular axis. The practical example may be tension compression members like trusses, shaft subjected to torque, connection of the elements. Then bar elements, it supports all the 6 degrees of freedom, that is translation along XYZ axis and rotation about XYZ axis. It is applicable only for symmetric cross sections. The practical examples can be stated as shaft subjected to multi-axial loading, bolted welded joints, connection elements, etc. Same as bar, beam elements, beam 1D elements, same as bar, but also somewhat unsymmetric cross sections, shear centers and warp edges. Then same as bar, the practical application, but for plus additional to that for unsymmetric cross sections also. Then pipe elements, same as beam, except it has internal non-zero dia, that is it's a hollow. Then practical application is piping system structural analysis. Then axisymmetric shells, they only support Z axis of symmetry, X as radial axis, for object symmetric about the axis of rotation and subjected to axisymmetric boundary condition. Thin shell pressure vessels, cylindrical, conical objects, etc. Then we discuss about 2D meshing. The basic question is when to use 2D elements. 2D elements are used when 2 of the dimensions are very large in comparison to the third dimension. The element shape for 2D elements are quad and tria. Additional data from the user are remaining dimension, that is the thickness. As you can see, the thickness which we give as the user defined value. Then the element types available in HyperWorks is thin shell, plate, member, plane strain, plane stress, axisymmetric solids, etc. Then practical application is sheet metal parts, plastic components like instrument panels, etc. Then why is 2D meshing is carried out on the mid surface? Quite often the geometry of thin walled 3D structure as shown in the image below is simplified to a geometric model with lower dimensionality. This is typically called as mid-surface model. The mid-surface model is then meshed with 2D elements. Thus, there is no need for a detailed volume mesh as the thickness of the geometry is virtually assigned to the 2D element. Mathematically, the element thickness specified by user is assigned half in plus z, as you can see for this model, plus z direction, and the other half in negative z direction element bottom. So that's why we create mid surface to perform 2D meshing. Then the family of 2D elements or different types of 2D elements available in HyperWorks is tria and chord. There are further classification for tria and chord is constant strain triangles, that is linear triangular elements, or linear strain triangles, that is parabolic triangular elements. They are also known as first order tria elements and second order tria elements. In second order tria elements, the number of nodes increases, so the number of interpolation points increases. Same the classification is for chord. Linear chord having 4 nodes, parabolic chords having 8 nodes. Then the most important part is how not to mesh. There are different rules generated or assigned by the industry that how not to mesh, which start with back-to-back triangles should be avoided. 2 tria elements should not be connected to each other directly, as you can see in the circle regions, that 2 triangular elements should not be connected back to back, as they increase the stiffness. Triangular elements are more stiffer as compared to chord. On a plane surface, triangular elements should be avoided. The reason is same, they are stiffer, so and they can also deviate the mesh flow lines, so it should be avoided. In the planar, if it's possible, go for the chord elements. No mesh transition or constant radius fillets or curvature. The mesh transition should be carried out on the planar surface. So in the fillets, there should be no mesh transition. It should be either on the planar regions, because it may or may not come under the high stress region. Avoid tria elements on outer edge or holes. So at the outer edges, because those are the failure regions, so avoid here, and around the holes also avoid the triangular elements. What is not acceptable at professional level is this type of meshing, which is not structural or flow. What is acceptable is this, with a proper flow of elements. Then circular holes should be modeled carefully with a washer 1.5 to 2 times dia and a minimum of 2 layers around the hole, as you can see, so that the interpolation will become strong and the results will be more accurate. Holes should be modeled with an even number of equally spaced elements. For a better representation of hole geometry and smooth mesh flow lines, hole should be modeled with an even number of elements like 6, 8, 12, 16, etc. rather than 5, 7, 9 and 13 to get a perfect hole-like structure. Nodes should lie properly on the surface with no deviation and no kinks. So as you can see, there are some kinks. So these nodes are coming out of the surface. So this should not be done. It should be properly on the surface. Switch, how you can see that in HyperMesh, switch off the element mesh line and observe the contour, in particular at curvatures. Kinks as shown above are not acceptable. follow the feature line, node should lie exactly on the edge. So you have to follow the surface feature lines maximum time. That you have to keep in mind that you have to follow the feature lines. That instead of zigzag distribution, a structured or smooth mesh is recommended. Node align in a straight line. Use the smooth option available in HyperMesh provided by most of the softwares. Helps in achieving systematic mesh. So this type of meshing is not allowed in professional. The mesh is perfectly in flow. For crash analysis, flow of the mesh flow line required. So it has to be perfectly in flow. For crash analysis, rotating cords are not allowed. As you can see, this type of structures are not allowed for crash analysis. For crash analysis, constant mesh size by using trias is preferred due to minimum element length and time step criteria. So this type of structure is allowed instead of this one. Then we will start move towards the 3D meshing. So again the question is when to use 3D elements. So 3D element should be used when all the dimensions are comparable. That is, all the 3 dimensions are comparable, then only we use 3D elements. As you can see in this, that is X, Y, Z, all the 3 are comparable. The element shapes available for 3D element is tetra, penta, hexa and pyramid. Additional data from the user required is nothing because we create the elements in all the 3 dimensions itself. Here the element types are solid. Practical application is gearbox, engine block, crankshaft, etc. These types of things which are modeled using solid elements. Then the different types of 3D elements, or you can say family of 3D element, includes tetra element. They are classified again like linear tetra having 4 nodes at the corner, or a parabolic tetra having 10 nodes, additional nodes at the mid side of their edges, of the elemental edges. Then penta elements, linear penta having 6 nodes, parabolic penta having 15 nodes, hex or brick meshing or brick element having 8 at the nodes, 8 nodes at the corner, or 20 nodes in the parabolic hex element. Then we will come up with degree of freedom for solid elements. Like for 2D thin shell and 1D beam elements supports 6 degrees of freedom, like 3 translational and 3 rotational, that is translation along XYZ and rotation about XYZ axis. But all solid elements have only 3 translational degrees of freedom, no rotational degrees of freedom. That is, a 10 noded tetra element has only 10 into 3, that is 30 degrees of freedom. Why does a solid element have only 3 translational and no rotational degrees of freedom? Let's physically interpret that. Consider a piece of paper, 2D geometry or long, say it's a 2D geometry, like, or a long steel scale, that is a 1D geometry. It could be easily bent or twisted, that is rotational degrees of freedom. But now consider a solid object like duster or paperweight. It could not be subjected to very high bending or torsional stiffness. Hence, solid elements have been formulated with 3 translational degrees of freedom and no rotational degrees of freedom, as you can see in the images. Then how not to mesh for 3D meshing? First point is mid node should lie exactly on the geometry. For a parabolic, that is second order tetra meshing task, many CA engineers prefers to start with linear tria, that is first order, instead of parabolic meshing, and then convert it into parabolic, that is second order. In the conversion process, mid nodes might not get projected automatically on the curved surface and fillets. If so, it should be projected on the corresponding surfaces before conversion to tetras. So the midpoint should project particularly on the surface, as you can see here. When the job is split among several engineers, the element length and the overall mesh pattern should be consistent. The above job was split among 3 engineers due to very short time duration provided by the client. The same mesh size and pattern was not followed by the engineer working independently on subparts of the geometry, as you can see here. So the mesh element size is different. So it should not be like this. If you split your geometry and divide it into n number of users to do a same part, the splitting portion should be meshed first, and all the other engineer has to start from that region. So the mesh consistency will be there. Then minimum 2 elements on the fillet of the tetra meshing. Elements at the fillet and curved surface usually fail, as you can see here. So 2 elements, 1, 2 at the fillet. So elements at the fillets and curved surfaces usually fails in the Jacobian distortion element check. The manual adjustment and improving the element quality results in mesh deviation from the geometry and visible kinks. This could be avoided by modeling the fillets with 2 or more elements. Then for brick meshing, a minimum of 2 elements across the thickness should be used. A single element leads to a poor interpolation and thus affects the accuracy of result. A minimum of 2 elements across any thickness is recommended. The exception in NVH application, where the stresses is not the main criteria, but the representation of mass and stiffness with the least degree of freedom is the main criteria. Use of tetra pentra pyramid element while brick meshing. Some clients allow for a few tetra elements during brick meshing. Also, some softwares and analysis type supports pyramid elements like HyperWorks. Uses the tetra and pyramid elements can make the life of the brick mesher tolerable. It's good practice to clarify the instruction for the use of these elements from the client. As you can see, pyramid or tetra. Modeling a sheet metal part with 3D element. For sheet metal, a very small thickness part, 2D shell elements are better suited for and recommended. It is not like we cannot use 3D mesh, but it will result in very high number of nodes and elements. Considering the following sheet metal part, we will mesh the same part with 3D parabolic tetra element and 2D quad 4 linear element using the same element length and compare the number of nodes and elements needed. So for 3D tetra mesh, the number of nodes is 1496 and elements is 689, while for the same component the number of nodes is 1 to 1 and elements are 100. So you have to decide which component you want to go for 3D and which component you want to go for 2D. Limitation of 1D element and advantage of 3D meshing. Fillets, cutouts and complicated geometry features cannot be represented accurately by 1D element. 3D element, because of 3 dimensions, can capture all the minute details accurately. For example, considering the following shaft, it is very difficult to capture the keyway slot and variable fillet using 1D element. Instead, 3D meshing is recommended for such applications. Then we will move to elements quality check. So now we'll discuss about elements quality and check. So element quality is a subject often talked about and never fully understood. The reason for this is complex but is related to the fact that quality is relative and the solution by definition is approximate. In the formulation of finite element, a local parametric coordinate system is assumed for each element type, and how well the physical coordinate system, both element and global, matches the parametric dictates element quality. Below you see some graphic representation representing element quality, and you should attempt to follow them. However, there will be a point of diminishing results if you try too hard to get every element within the acceptance criteria. Your judgment is your only guide in those cases. Always perform quality check on the meshes you create. Check with local experts regarding the appropriate values for each element type required by your element checking computer program. Beware that in this situation, correct answer can vary a great deal, as illustrated in the following table, where the range between OK and very poor is quite wide. Solid elements use the determinant of the Jacobian matrix and compare to the ideal value. Some common element quality measures are detailed below. The best element 2D tria is 60, 60, 60 and all the sides are same. OK is right angle tria and somewhere two sides are equal, one is different. Very poor is like the third one with a 10 degree or a 105 degree angle. Same for the quad. Perfect is perfect ideal square. Then a rectangular and some other changes in the side or angles, and very poor is the 30 degrees angle triangle quadrilaterals. So we'll discuss some important quality checks like skewness. Skew in trias is calculated by defining the minimum angle between the vector from each node to the opposing mid surface and the vector between two adjacent mid sides at each node for the element. As you can see here, 90 degree minus the minimum angle found is reported as skewness. Skew in chord is calculated by finding the minimum angle between two lines joining the opposite mid sides of the element. 90 degree minus the minimum angle found is reported. The skew check is performed in same fashion on all the faces of 3D elements. Then aspect ratio. Aspect ratio in two-dimensional element is calculated by dividing the maximum length side of the element of an element by the minimum length side of the element. The aspect ratio check is performed in the same fashion on all the faces of 3D elements. Warpage. Warpage in two-dimensional element is calculated by splitting a quad in two trias and finding the angle between the two planes which the trias form is then found. The maximum angle found between the plane is the warpage of the element. Warpage in three-dimensional element is performed in the same fashion on all the faces of the element. Then now we will discuss about some detailed quality checks by taking 2D quality checks first. For 2D quality checks, the ideal shape for quad element is square. The ideal shape for triangular elements is equilateral triangle. Different quality parameters like skew, aspect ratio, include angles, Jacobian, stretch, etc. are the measures of how far a given element deviates from the ideal shape. A square means that all the angles are 90 degree with equal sides, while an equilateral triangle has all the angles at 60 degree with equal sides. Some of the quality checks are based on angles like skew and included angles, while other on side ratios and areas like expect and stretch. To reduce the solution time, elements are mapped to local coordinate system individually for every element at the centroid. Instead of using a single coordinate system, that is the global coordinate system, the effectiveness of this transformation is checked by the Jacobian and distortion. Ideally, all the nodes of the quad element should lie on the same plane, but because of curvature and complicated geometry profile, it is not possible. The measure of the out of plane angle is the warpage angle. So the warpage angle is the out of plane angle. Ideally, it has to be 0, but acceptable value is 10 degrees. Warpage angle or the wrap angle is not applicable for triangular elements. It is defined as the angle between the normal of two planes formed by splitting the chord elements along the diagonal. The maximum angle of the two possible angles is reported as warpage angle, as you can see. So this is the warpage angle, and if we extend this is the warpage angle. Then aspect ratio for 2D elements is the maximum element edge length divided by minimum element edge length. Ideally, the value should be 1, but the acceptable range should be less than 5, the ratio. As you can see, the maximum length to minimum length ratio should not exceed 5. Then skew. Ideal value of skew is 0, but acceptable is less than 45 degree. Skew for quadrilateral element is 90 degree minus the minimum angle between the two lines joining the opposite mid sides of the element. Skew of the triangular element is 90 degree minus the minimum angle between the lines formed each node to the opposite mid side and between the two adjacent mid sides at each node of the element, as you can see here. Jacobian, the ideal value of Jacobian is 1, but acceptable should be greater than 0.6. In simple terms, the Jacobian is a scale factor arising because of transformation of one coordinate system to the other. Elements are transformed from global coordinate system to local coordinate system defined at the centroid of every element for faster analysis time. Then include angle, that is very important. Like skew is based on overall shape of the element and it does not take into account the individual angle of quadrilateral or triangular element. Included or interior angles check is applied for individual angles. For quadrilateral or the quad, ideal value is 90 degree, but the acceptable range is 45 degree to 135 degree. For tria elements, ideal value is 60 degree, but the acceptable range is 20 degree to 120 degree. Then minimum element length. This is very important check for crash analysis, that is time step calculation. It is also applied in general to check for the minimum feature length captured and the presence of any non-zero length element. So if in minimum length, if anyone is getting 0 length, that means the feature is going very worst, that particular element. So we have to remove that. Then chord deviation. This helps in determining how well curvatures have been modeled. It is defined as the distance between the midpoints of an element edge to the curved surface. It is not applicable for linear elements. Then how to improve the quality of poor elements. There are different methods to improve the quality of poor elements, like manual adjustment. This is done by translating the nodes manually or remeshing in the poor mesh region. The method consumes a lot of time and was the only technique available for years. Drag node. The user has to drag the node of the failing element it works faster, and the advantage is that it instantaneously shows the effect of dragging the node on all the attached elements. Auto quality improvement programs. This is the latest option for quality improvement. The user has to submit the mesh for quality improvement, and software program runs in the background to improve the elements quality automatically. So these are the different options available in HyperWorks to improve the poor element, the quality of poor elements. Then some other checks for 2D meshing is element free edges. What is free edge? Any single quad element has 4 edges, as you can see here. 2 element in the case above, the middle edge is the shared and is no longer a free edge. You can see here. For a real FEA model, free edge should match with the geometry outer edge, that is free edges. Any additional free edge are an indication of unconnected nodes. So the free edge should be at the outer edge of the surface. Any in between free edge means there is no connectivity or unconnected nodes, so it should be avoided. We have to be properly connected, otherwise the forces and constraint will not get transferred from one portion to another. Then duplicate element. Mistakes during the operation like reflect or translate can result in duplicate elements. These duplicate elements do not cause any error during the analysis, but increases the stiffness of model and result in small displacements and stresses. For example, consider a simple plate thickness 2 mm subjected to a tensile load. Assume that due to some meshing operation, all the elements are duplicate. If the analysis is carried out, then it will show half the stress and displacement. Then duplicate nodes. Operation like copy, translate, orient or reflect can result in duplicate nodes at a common edge. In the above image, there are duplicate nodes at the interface where the mesh was reflected. The duplicate nodes are highlighted in yellow. Then geometry deviation. After the completion of meshing, the mesh and the geometry should be viewed together. Mesh line option off. The mesh should not deviate from the geometry. Delete free temporary nodes. Free nodes, if not deleted, results in rigid body motion. When the auto singulatory option is turned on, the software uses a spring element with a very small stiffness to connect the free node with the parent structure. This results in warning message during the analysis. Renumber nodes, elements, property, etc. before export operation. Frequent import-export operation could lead to a very large number for nodes and elements IDs. Some software refuses to read the file in the node or element. IDs are greater than a specific limit. This could be avoided by renumbering the nodes and elements. Observe type, family and number of elements. Element summary for complete model. The mesh should be checked carefully prior to the export operation as well as after importing it in the external solver for element type, family, number, etc. Sometimes due to translator program, if properties are not defined properly or for non-supportive elements, either the element are not exported at all or the family is changed, like membrane element converted to the thin shell, etc. Plot, trace line, element free edge or free face, if any, should be deleted. Check mass. Actual mass versus FE model mass. When a prototype or physical model of a component is available, the FE model mass should be compared with the actual mass. A different A difference means that there are missing or additional components or improper material or physical properties. Free run or dummy linear static analysis. Before delivering the final mesh to the client, a free run should be performed. 6 rigid modes indicate that all the parts in the assembly are properly connected to each other. In the case of a single component meshing job, a linear static analysis with a dummy boundary condition should be carried out to check the mesh quality, mesh connectivity. Request your colleague to check the model. Due to continually working on the same project, your mind tends to take some of the things for granted, and there is a possibility of missing some of the points. It is a good practice to get it cross-checked by your colleague prior to finally delivery. Then we'll discuss quality checks for Tetra mesh. First we will start with TET collapse. The ideal value is 1 and the acceptable is greater than 0.1. Tetra collapse calculated as H multiplied by 1.24 divided by A. It is defined as the distance of node from the opposite face divided by area of the face multiplied by 1.24. Other checks are same for the Tetra elements as 2D one, that is Jacobian and included angles and everything. The other checks for Tetra meshing is quality check for 2D tria element. Before converting trias to Tetra, all the quality checks as discussed for the shell element should be applied. Free edge conversion from tria to Tetra is possible only when there are no free edge. No free edge indicates the mesh is in a enclosing volume. T connections. A mesh model should not contain any T connections for Tetra meshing, as you can see here. This is the geometry. T connection not acceptable. Green element should not be there in the model. No T connection, corrected mesh. Consistent shell normals. Before converting trias to tetras, the shell normal should be corrected. Some software do not allow shell to solid conversion unless the normals of all the elements are properly aligned. Geometry deviation. After the completion of meshing, the geometry as well as mesh should be viewed together. Mesh line option off. The mesh should not deviate from the geometry. In the process of quality improvement, in particular for distortion, Jacobian on curved surface or fillets, sometimes node get translated too far away from the geometry and is not acceptable. 2D tria element should be deleted before the final submission. It's a common mistake to export 2D shell elements along with the Tetra mesh in the final delivery. Then we will discuss about brick mesh quality checks. The ideal shape of the brick element is cube. Various quality criteria check how far a given element deviates from the ideal shape. Warpage angle. Ideal value is 0 and acceptable should be less than 30 degree. Warpage angle is calculated on face of the quadrilateral element of a hex element. It is the angle between the plane that formed by splitting the quad element. Jacobian. Ideal value is 1. Acceptable should be greater than 0.5. In simple language, the Jacobian is a scale factor arising because of transformation of the coordinate system. Elements are transformed from global to local coordinates to reduce the solution time. Aspect ratio. Ideal value is 1. Acceptable is less than 5. Aspect ratio is equals to maximum edge length divided by minimum edge length. Quad face include angle is 45 degrees to 135 degrees. Tria face include angle is 20 degree to 120 degree. Number of percentage of pentas acceptable for a brick meshing should be less than 5%. Other checks for brick meshing: free faces. A free face check is the most important check for brick meshing. A single brick element has 6 free faces. Free faces of the mesh should match with the outer surface skin of the solid part. Any extra inside faces indicate that either nodes are not connected properly or there are mismatching elements. As you can see, this is the brick machine, free faces. At the inner side you can see the free face inside also, so it is not connected. Also, converting the free faces to tetra. For complicated geometries, checking the internal free face could consume lot of time. A quick shortcut is to convert the free face to tetra mesh. Successfully conversion indicates that the brick mesh is okay and there are no internal faces. So instead of finding it for the complicated geometry, the inside free faces, you can directly convert that into tetra. If it converts into tetra, that means there are no free edges. Then the last topic of today's webinar is material and property information. So the material classification we will discuss with isotropic. Iso means same, tropic means direction. Isotropic has the properties independent of direction or axis. Two independent constant, that is E or nu. They are mostly metals. Orthotropic. Ortho means 3. Tropic means direction. Different properties along 3 axes. 9 independent constant. Wood, concrete, rolled metals, etc. Anisotropic. Different properties along crystallographic plane. 21 independent constant. All real life materials are anisotropic only, but we simplify them into the category of isotropic and orthotropic. Laminates. 2 or more metals bounded together in layers. Simplest example is lamination carried out on certificates, identity cards, etc. Mainly used for space applications, and these days in automobiles the trend is shifting towards plastic and laminates from metal, as you all know that. Then material properties. This is the table which discuss the modulus of elasticity, Poisson's ratio, density, yield strength and ultimate strength for different materials like steel, cast iron, wrought iron, aluminium, aluminium alloy, brass, bronze, copper, copper alloy, magnesium, titanium, glass, rubber and concrete. You may be discussing that why mass is in ton and density tons per mm cube for Newton mm unit system. So the explanation for this is 1 Newton is equals to 1 kg into 1 meter per second square. F is equals to ma. So 1 Newton is equals to 1000 kg multiplied by 1 mm by second square. So 1 Newton is equals to 1 ton multiplied by 1 mm by second square. Hence, when force is specified in Newton, length is in mm, mass must be specified in tons and density in tons per meter cube. The different systems for steel is, for SI the length unit is meter, mass unit is kilogram, time unit is second, force unit is Newton. For MTS system, length is mm, mass is ton, time is second, force is Newton. For mm, kg, ms system, length is in mm, mass is in kilogram, time is in milliseconds and force is in kilonewton. So the Young modulus will change, as for SI system it is 210 e to the power 9, For MTS, it's 210 e to the power 3, and for mmkg ms, it's 210. Same, the value changes for density, but the Poisson's ratio remains the same. It is a unitless quantity. So whenever you enter the material properties in software, make sure you enter the correct material properties to get the perfect results. In this way, I have ended the first day session of this 10-day HyperWorks training. Thank you very much for attending this session. To apply for the free e-copy of the book, please visit http://www.altieruniversity.com/student-guide-request. To improve the online training session, please help us by sharing your valuable comments at edusupport@india.altier.com.